Alright. Hello everybody. I am just getting everything set up here, so if someone could drop something in the chat to let me know if they hear me, if my audio is too loud, too quiet, whatever, that would be super. Alright, Sergey, I'll add piecewise functions to the to-do list. Okay, perfect. Alternating series error bound limit comparison test. Okay, yes, we'll go over that when we get to the interval of convergence item in the to-do list that you can see on the screen. I'll make sure I get to that. So, yeah, we're just going to get started. What I'm going to do for the format of this is I'm kind of going to jump around. I've put things on the to-do list roughly in the order in which they were requested of me. So if I got a message earlier, that topic is at the top of the to-do list and so forth. That means that I'm probably going to be jumping pretty quickly from Calc AB to Calc BC, etc. So if there's something that you're super comfortable with, or maybe you don't recognize, that could be because you're in BC and we're covering an AB topic, or vice versa. So don't be alarmed for those of you in Calc AB looking at the to-do list, wondering what in the world integration by parts is, or interval of convergence. I'll let you know exactly what test things are pertinent, what test each topic is pertinent to before we really get going into it. So the first thing that we're going to cover is something that people in Calc BC are probably painfully familiar with, but those of you in Calc AB might need a refresher on. So that's going to be finding a line tangent to a graph. That and implicit differentiation are both covered in this free response question, which was sent to me by a user. So I'm going to start out by taking a look at this. I'm not sure what year this is from. I didn't look it up or anything. Yes, Daniel, I'll add Polar to the list. Okay. So, just a rough overview of what we've got going on for creating lines tangent to a graph. In order to create a line tangent to a graph, we're going to need a point on the graph and the slope of the graph at that point, the derivative of the graph at that point. So what that means is if we have a function that looks something like this, and we want to find our line tangent to the graph at this point, then we're going to need this point on the graph as well as the slope of the line tangent to the graph at that point. So in this function, which is going to be a implicit differentiation problem, actually I want to see what year this is from, because this is this looks like it's from, I feel like I recognize this problem. Okay, it looks like this is from the 2015 Calc AB test. So this is good. If you're in Calc AB, perfect. Yeah, I think it's from 2015. All right. So what we're given in this problem is the first derivative, which will allow us to find the slope of the tangent line. And for part A, we're actually given a point. So those two things will allow us to come up with the equation for our tangent line. So the first thing we'll do for part A is take this point that we're given in the problem and plug it directly into the derivative to find what the slope of the line is. So the notation that I'm going to use for this that you've probably seen in your calc book, but has been new to some people that I've worked with, is the derivative. This line here that you'll see is basically math writing for evaluated at. So I'm going to say this function evaluated at the point -1, 1. This just means that I'm going to plug in -1 for all the x's and 1 for all of the y's in this function. Alright, so just following from this function right up here, I'm going to plug in -1, 1. So we'll have 1 for y over 3 times 1 squared minus -1. And with some algebra, we get 1 over 3 plus 1. Now this here will be the slope of our tangent line. So we'll be able to use that in conjunction with the point to come up with the line. So using the point slope formula, we'll have y minus 1, plug in our slope, x plus 1, and this would be sufficient for credit there. This can be done on any curve as long as you can, if you know how to take its derivative, you can find the slope of any line tangent to the graph at a particular point using these same steps. So next, to sort of generalize on that idea, the problem asks for the coordinates of all points on the curve at which the tangent line to the curve at that point is vertical. Oh, looks like it got cut off here, so vertical. Okay, so we know that the slope of a line is, like when the slope of a line is undefined, that line is vertical. So when basically, if we have a slope of, say, 1 over 0, 3 over 0, 9 over 0, whatever, that will give us a vertical line. So what we're going to do here is look for values for the derivative, or is look for basically what we're going to see what makes the denominator of our derivative equal to 0, because that will mean that our derivative is undefined, meaning the line tangent to the curve at that point is vertical. So to do that, we're going to just look at the denominator of our derivative, 3y squared minus x, and set that equal to 0, because we're going to be looking for things that make our denominator equal to 0. So 3y squared minus x equals 0. Simplifying from here a little bit, we'll see 3y squared equals x. And so now we know anywhere where x is equal to 3y squared on this graph, at these points we're going to have a tangent line of vertical slope. So what we can do with this is couple that with the original curve that we were given, y cubed minus xy equals 2. And take this value of x that we found over here, 3y squared, and plug that back into our original curve. That will allow us to find, we're basically solving an equation. We're solving a system of equations at this point, because we know for all points x, y, such that this equation is satisfied, we have a vertical tangent line. So we're going to take this and just plug it right into here. We'll get y cubed minus plugging in 3y squared times y equals 2. I'll just kind of speed through the algebra here a little bit. We'll have so from there we can deduce that y equals -1. Taking this and substituting it back into our curve, we'll get so now these two things here, these two values we found for x and y, have given us the answer to the question, or the point at which the tangent line is vertical. So we have 3, -1. That would be our answer for part B. So now we're going to move on to part C, which looks intimidating at first, but actually brings in a strategy that is used very, very frequently on the AP Calc exam and the free response questions to make things easier rather than harder, and that is looking at work that you've already done. So I'll show you exactly what I mean by that. This question, it asks for the second derivative evaluated at the point on the curve where x equals 1 and x equals -1 and y equals 1. That's just them writing, or like the point on the curve where x equals -1 and y equals 1 is just another way of saying like on the curve at the point -1, 1. We already know the first derivative at this point, so we're actually going to use that when we evaluate our second derivative using implicit differentiation. So I will show you that now. I don't have enough space at the bottom, so I'm going to go to the back of this. Remember, you can feel free to pause this stream at any time. There will probably be some topics later that if you want to catch up with, or that you don't need to, there'll probably be some topics later that you don't need to catch up on, so you can just like go back to the live stream at that point if you want to like go over and review these. Also, each time I finish a problem, I'm going to take it, scan it, and upload it to Google Drive at that link that you can see at the bottom of the screen. So you'll be able to go over all of my work in more detail and probably higher resolution than what you can see on the screen right now. So anyways, I'm going to go to the second derivative. So we're going to be taking the second derivative evaluated again at -1, 1. So we know our first derivative, or we'll get to this part in a second. I'm actually going to work up. Our first derivative was given in the problem as y over 3y squared minus x. Now, implicit differentiation on this, combined with the quotient rule, will allow us to find the second derivative, and I'll kind of walk through that here. So essentially, taking the derivative of each side, this left side will be just our d squared y over dx squared, just our second derivative notation, equals, and now this is where the implicit differentiation is going to come in. We're going to use the quotient rule. So people learn different things for this. I learned sort of a mnemonic device in my calc class, which sounds a little bit silly, but has kept the quotient rule in my head for many years. And that was ho d high minus hi d ho over ho ho. Okay. Okay, I think we're coming back. We're coming back! Alright, we back. Yeah, it's good. Okay. What? Okay. Alright. Yeah, I don't know what happened there. Gotta love Comcast. Okay. So. Hody high was too powerful. Okay. So yeah, I see some people. Lodi high. Yeah, my calc teacher was a little wonky to whoever said it was Lodi high and Heidi low. It was definitely Hody high, Heidi ho, according to my absolutely nutso calc teacher. So anyways, going back to our thing here. So we've got the bottom times the derivative of the top minus, we'll have the top times the derivative of the bottom, basically the opposite. So y times the derivative of the bottom, which using implicit differentiation, we'll take the power rule on this 3y squared minus x. That'll become 6y, and then because we're using implicit differentiation, will be dy dx. I'm sorry about this, everybody. This is very... Oh, it's back, it looks like, maybe? Hoping. I'm going to put related rates in the to-do list right next to optimization, because that's roughly, it's like a similar topic. Okay, cool, we're back. That's good. All right, hopefully it sticks around this time. So, finishing up this problem real quick, because I want to make sure I can get to as much as possible. We'll take our top times the derivative of the bottom using implicit differentiation. And we'll have this over ho-ho, which is just the bottom squared, or low if you're pleb. Okay, so now this is where the difference comes in for, like, this is why we can use those other results that we got in part A of this problem to help us out here. If you were strictly finding the function for the second derivative, you would have to take this dy dx, plug it into here, and then have to do some absolutely disgusting algebra to simplify everything. But because we've already evaluated dy dx at -1, 1, we found this, our result from part A, which I'll do in pink. This evaluated at -1, 1, well, that was equal to 1/4. So what we can do is just plug in -1, 1 anytime we see a dy dx, which will be here and here, and plug in our -1 and 1 into all of our y's and x's, do a bunch of algebra, and we should be able to simplify to our answer. So I will run through that real quick for you. Okay. Oh, I like that. Low d high minus high d low, all over the bottom squared we go. Or you can do ho d high minus high d ho over ho ho. That's a good one too, I heard. Alright, 3 times 1 squared plus 1. Alright, so we got a bunch of garbage here. We'll simplify that. This will go to 3 plus 1, so 1 minus 1 times 6, okay. 6 over 4 will be 3 over 2 minus 1. This will all be over 4 squared, or 16. 1 minus 1/2 will be 1/2. All over 16 equals 1 over 32. And that concludes this problem. Low d high less high d ho all over low squared u ho. I think that beats out ho d high minus high d ho over ho ho. Thank you, Ethan. Okay, so I'm gonna take this real quick and scan it. I'm gonna hold on. I gotta make a little index card thing if I can find them. Alright. Or, yeah. Okay, so I'm going to scan this real quick, adjust the to-do list, and get another problem ready. So, alright. Alright, so, alright, we're going to cover a lot. We're going to cover like all of calc tonight. Alright, Riemann sums. That's going to go, where can I put that? I'm going to move this. Alright. Alright, so almost done with the scan. Okay, yeah, so Stargamer39 pointed out something important. Yeah, okay, actually, I'm a bit of a hypocrite because I tell people to do what he just did and I didn't do it myself there. Once you plug in the x and y, I'll show you exactly where. This here would actually suffice as an ant. Here, hold on. I gotta. Where am I gonna add Riemann sums? Here. I'll do Riemann sums and what was the other thing? I'll put that right forward. Solids of rotation, I believe they're called. Okay, so this here. This would be an acceptable answer. As well. Okay, so now, what in the world, Garrett? Alright, so I'm going to make a new calc review folder. I'm going to get this a lot more streamlined in a couple seconds. If it's multiple choice, you will need to simplify to find yes. But if it's free response, you will not need to. Yeah, you got it. So this was okay, so I'm going to put this in Do you guys have access to that Google Drive link that I posted, by the way? I want to make sure the /calc review. Someone could let me know in the chat if they have access to it. I'm actually going to put a PDF in there real quick, and you guys can tell me if it's accessible to you. Okay. The Ultimate 9, you can stop simplifying in FRQs the second that all the numbers are in there. If there are no more variables in the equation that still need to be like substituted with actual numbers, that's good enough to stop simplifying. That's why you can leave things in point-slope form versus changing them to slope-intercept form, as some people like to do. Okay, and yeah, this would be sufficient as an answer as well for part C of this problem. So can someone check to make sure that that PDF shows up in the exam reviews folder? If so, then I'm going to move on to our next topic, which will be separable differential equations. All right, sweet. Cool, so let's move on. Okay, so next will be, let me find a solid separable differential equations problem, unless somebody has one ready to go. Let me see if I can find a good one. All right, so I'm gonna keep this card around. Yeah, I heard the physics C test positively slaughtered a lot of my friends. So, all right. So I should put headings on these. I'm gonna start doing that. All right, so let me find a wow, this is, oh man, I stumbled on a teacher's guide. Okay, if anybody has a good question, I'm not sure who requested separable differential equations, but if you're in here and you want to either PM me a link to one that you want to look at, or just post it in the chat, that'd be cool. I will get to the Lagrange error bound. Yeah, that will happen. That's on the list. Or I guess I'll add that. I'll add that on I'll add that to the to-do list. Okay. I'm responding to a few. Okay, so now, free response questions. I'm sorry this is taking so long, guys. If you guys prepare questions and actually send them to me on Reddit for me to do, that would probably be a lot better for making this happen. Okay, so okay. Yeah, I'll do that. Well, actually, separable differential equations, the issue with doing that, Max, is that some of these are actually going to be both AB and BC. Okay, so what I'm going to do, I'm going to look at actually another, okay. All right, here's what I'm going to look at. I'm going to look at a problem. Let me print this, actually. This will be from the 2016 free responses. My computer is lagging quite a bit right now. It's got a lot of stuff going. It's an old thing. Okay. So this is printing right now. Yeah, separable will be on both. I believe the problem that I'm going to do right now, I'm pretty sure was, if I had to guess, probably on both the AB and BC tests. And that is true for several of the FRQs. A lot of them will be on AB and BC. I think, I'm not sure if it's 3 of them or 4 of them are shared. There's some number. And as you know, if you're taking BC, there is an AB subscore, so knowing how to do all of the AB topics that are also a requirement for doing all the BC problems will get you a score as though you had taken the AB test. So I wish my printer would work. I can just do this without a printer, I think. Oh, here it goes. Okay. So, spit it out. Okay. All right, sweet. So, looking at this differential equation, we're going to do a slope field, find a particular solution, and yeah, perfect. So, okay, Easton. All right, so just sort of for the slope fields, you can kind of just plug in all of these values for the derivative. I'm not really sure how to teach this per se, but I'll do my best. I guess basically you're going to take this point 0, 0, plug it in up here, see what slope you get, draw a little line. I'm going to do it in pink so it shows up. Basically we have 0, 0. When we plug 0, 0 into here, we get 0. So you put that there. Same thing here. I just know that because y is 0 on this line, and when I plug 0 in for y up here, the entire thing is going to go to 0. When I plug in 0, 1, I'll have 1 over negative 1, so that'll be negative 1. When I do 2, 1, that'll be 1 over 1, or just 1. Coming up to here, when I do 0, 2, I'll have 4 over negative 1, so negative 4, kind of like something like that. And then 2, 2, I'll have 4 over 1, which will just be something like that, and that's enough to get credit. Yeah, I know, me too, Michael. Okay, so I'm going to copy this differential equation down to here so that we can know what we're referencing. Okay, so next we're asked to let f of x, or let y equals f of x be the particular solution with the initial condition f of 2 equals 3. Write an equation for the line tangent to the graph at x equals 2, and use your equation to approximate f at 2.1. Okay, so this is actually going to be what we just did. It's going to be finding an equation for the line tangent to the graph. So we're given our point x equals 2. We know that 2, 3 is a point on the graph from the question. So we have 2, 3. We can plug in 2, 3 into our equation here. should specify this is for b, evaluated at 2, 3, will be 3 squared over 2 minus 1, or 9. So this will be our point. This will be our slope, from which we can create our point slope equation. Y minus 3 equals 9 times x minus 2. Now this is your equation for your, this is the equation for the tangent line. Now to use that to make an approximation for f at 2.1, we're going to plug in x equals 2.1 to approximate. So what that'll give us is y equals 9 times 2.1 minus 2. Notice we're plugging in 2.1 for x plus 3. And that would be how it's finished out after you hash out the rest of the algebra. Okay. Yes, StarGamer39 is pointing out something that, useful in the chat, and that's to basically just create a little chart to help you find the slopes for these individual points. It's optional as long as you get all the. If that helps you to make everything, like for you to be certain about everything, then cool, thumbs up. Alright, so next we'll move on to part C, which is the actual separable differential equations, which is the meat of this problem. So we're asked to find a particular solution given that initial condition f of 2 equals 3. And just so I can zoom in here, I will write our equation down. Again, this is very... Hold on, I'm going to move my camera around a little bit. Okay, this should be good. So we have this, and we have dy dx equals y squared over x minus 1. Okay, so this is a separable differential equation. So what we're going to do is move everything involving the variable y to one side and everything involving the variable x to the other. And so what that's going to give us when we put the okay, I just looked at my phone. I saw a message from one of you about the solids of rotation problem, so I'll make sure to do that when I get there. Yeah, it's on there. Okay, so I'm going to move all the y's over to here and all the x's over to here. What that will give me is 1 over y squared dy, basically dividing both sides by y squared, is equal to, when I bring this dx over to here by multiplying both sides by dx, 1 over x minus 1 dx. So basically, what you can kind of see here is like two things that are like super ready to be integrated. So what we're going to do with both of these is we're going to take the integral. So kind of drop those guys in there. What that'll give us, moving down to here, integrating 1 over y squared. This is something that I'm just going to use my power rule knowledge to do. Hopefully you guys have a handle on differentiation. We're going to have this. This is going to be equal to, again, this is something that you should know for the, yeah, it's if you have like 1 over u, or like 1 over x dx, you can turn that into the natural log of the absolute value of x minus 1. Whoa. Yeah, natural log. Whoa. Oh, hello, Daniel. You're excited. Okay, I'm going to put the plus c. Generally, it is good practice to, or like it's going to be useful to, or you should. It's not even a recommendation. Put the constant on the side with the x. When you're going to have both of these, typically when you do an indefinite integral, it's habit to add a constant. But what you're doing here is integrating with respect to x, so we're just going to put the constant on that side. That was a poor explanation. Just know that you're going to add the constant on this side. To the 1 over y is negative because here we're integrating. Here, let me do a little pink sidebar. We're going to make blue be the actual work on this stream and have the pink just sort of be the side work. This is basically integrating y to the negative 2 dy. So when we do the reverse power rule, we're going to, wow, yeah, these people are going crazy in the chat. Yeah, basically what we're going to do is decrease this by 1, or we're going to increase it by 1. So that'll go to like y negative 1, and we're going to put that like 1 over this exponent over here. So 1 over negative 1. I'm explaining this really poorly, but this is the way, yeah, just increase this, and then the constant out here becomes 1 over that exponent. Now that works for everything except y to the negative 1, as we know, because that has to go to the natural log. So we'll just leave it like that. Okay, so now we have this function here. And what we're going to do, because we have our initial condition, we remember up here, f at 2 equals 3. So we're going to take that, punch that into this equation so we can find out exactly what the value of c is. So negative 1/3 is going to equal the natural log 2 minus 1 plus c. So negative 1/3 equals 0. The natural log of 1 is 0 plus c. So c is going to equal negative 1/3. And so now what we've got, yeah, always remember c. Yeah, you need c. Basically, the way that they grade these is the second you forget c in your work, they just stop grading. Any points you get before that are kind of fair game, but most of the points that you're going to get are going to be after the integration part anyways, so definitely remember your constant. So now that we have c, we can find our general equation. So plugging c back in here, now that we've got it, we'll have negative 1 over y equals natural log absolute value of x minus 1 minus 1/3. And then all that's left to do is solve for y, which I'm going to do in one disgusting fell swoop here and just say y equals negative 1 over the natural log. And yeah, it's certainly not pretty, but it is an acceptable answer. And it is probably the answer that they're looking for on College Board if you go check it out. So that's going to be separation of variables. Cool. So with that done, if nobody has any questions, I will scan this and put it on the drive. Noah, all I have to say to you while I'm just like waiting for my computer to load is don't cry. Definitely don't cry. And to speak to the like notion of not crying, don't cry over multiple choice problems. If you get stuck for several seconds over a multiple choice problem, or if like you're just looking at it and you're just completely stumped, move on. You can do pretty well on the Calc AB exam even after missing a couple questions. So it's going to be more beneficial for you to to move forward and find other problems that you are comfortable with, that you know you can get correct, and then go back to the ones that you weren't so sure of immediately, than to just sit there, struggle, and eventually find yourself out of time at the end. So yeah, also don't get too strung out over the multiple choice and just end up being just completely fried by the time you get to the free response. That won't serve you well either. Okay, so I think this will be ready to upload. Let me just save it real quick, and we will move on to integration by parts. All right, cool. So integration by parts has been uploaded. Or no, damn it, did I name it integration by parts? I'm so stupid. Okay, hold on. This is... Okay. Go to the link on my Angel. Go to the link that you see at the bottom of the screen, the jmag.me/calc review, and you'll see what I'm talking about. Yes, very important. Do not leave a single question unanswered in the multiple choice. That's just bad news. Okay, so I will adjust the to-do list and we'll move on to integration by parts. I'm not really going to go over the theory of integration by parts so much as I am the actual use of it. Just integrate a couple things that you need it for. The reason that integration by parts works is actually a really neat way to understand it using the power rule. I don't think we have time to really go over that, so I'm just going to find a couple integration by parts problems. And we'll go over the no, yeah, you definitely would, Noah, because I'm going to do probably 3 or 4 of these problems. Also, this is a BC topic, so anybody that's doing AB, if you want to go back and look at those other 2 topics that we just looked at, then this would be a good time to do that. That's all I have to say. Okay, so integration by parts. At some point, probably after the Riemann sums, I'm going to go... let me add stuff to... I said I was going to add stuff to the to-do list, and I haven't done it yet. So, intervals of convergence, I'm also going to go over. Okay. I got you, Roshan. Yes, that is a good... That's the rule for... That's the rule for L'Hopital's, Michael. Okay, so. All right, integration by parts. Let's take a look. For this, I'm not gonna go find anything. I'm just gonna come up with some integrals. So this will be yeah, we're also going to get there. Yeah, we will get there, Eric. That's a... darn, I cannot for the life of me remember. Yeah, tabular method. Tabular method. Yes, we will do that as well. The tic-tac-toe method. I like that. Okay, yeah, we'll go over everything. So integration by parts. Let's look at a couple of examples. Probably one of the first examples of integration by parts that people see is the detail. That's good. We're going to try and integrate this. So what you're going to need to do for integration by parts to Jordan, for which question are you looking at? Jordan? Are you talking about the separable differential equations problem? Yes. Actually, I'm going to look at the to-do list right now and kind of move it around so that I can make sure we're kind of bouncing between A, B, and BC problems properly. So right now we're going to do BC. L'Hopital's and Riemann's will be probably mostly AB, because BC, you become very comfortable with that. It's like not really a topic that you need reviewing. On U sub is definitely both, so that'll be good. I'm going to take that position functions particle problems and sort of shove that in right before optimization. That'll be good, because that's a very quick thing. So we'll get there. Jordan, if you could clarify on what you're talking about, that'd be super. Okay, so what we're going to be looking for when we do integration by parts is a way to break this into a product. We're basically going to be looking for one thing in here which we can very easily take the derivative of, and another thing which we can very easily integrate. And we're going to regard the integrand. Yes, you will, Roshan. You do need a no-shell method. Sorry for cutting myself off there. You're going to regard the integrand as a product of those two things. So what we're keeping an eye out for right now is something that's very easy to take the derivative of, and something that's very easy to integrate, which form a product that is our integrand. So what we see here, this guy, this x, we can definitely take the derivative of that x. That's just a super easy thing to do that we're not going to have much trouble with. This guy, this e to the 3x, this we know how to integrate. So what we're going to do is call this u and call this v, and call this dv. And we're going to basically apply a formula. Let me get a different color for formulas. Let's give me my formula color. Let's use light green. Cool. So if you already know integration by parts, go watch Khan Academy about something you don't know, and hopefully come back to here when everything's done. All right. So integration by parts, our super important formula that we're going to need to know for everything, is u dv equals u v minus the integral of v du. Okay, so just to sort of like flesh out exactly what I was talking about, here we see that in on the right side of our equation, u is going to go to du. So we need to know how to take u's derivative. dv, we're going to turn into v on this side. So we're going to need to know how to integrate it. So what we're going to do here is basically just apply this formula. The dv is going to encompass this entire thing that I have underlined here. So we're just oh, that's great. I haven't seen that before. Sunshine minus Voodoo. Ah, that's cute. Okay. So, Sunshine minus Voodoo. That's great. Okay. So, we're just going to apply this formula. This is going to become UV. So, we're going to write everything out first. We know that we have U equal to X. So, du, that will be equal to just like 1 dx, just using regular Calc 1 stuff. Hell yeah, Edward. Alright, so we're also going to know, we also have dv. dv, we see right now, is equal to e to the 3x dx. And I'm hoping that if you're doing calc right now, you can, I mean, I don't know, I don't want to be presumptuous. The v is going to be equal to 1/3 e to the 3x, just using our regular integration techniques with e to the x. So now that we have all these pieces, we can take care of this integral. So this is going to be equal to, just like following our Sunshine minus Voodoo deal up here, we'll have x times 1/3 e to the 3x minus the integral of v du. So that'll be 1/3 e to the 3x du, which is just dx. Now this integral over here becomes something we can take care of with regular calc that we know. So this will become x e to the 3x over 3 minus 1/3 this guy we know how to do. That's going to be oh man, oh man, oh man, plus c. Can't forget the plus c. Someone should have called me out on that. Alright, cool. So that's an example of integration by parts. I'll go over, to sort of explain how the tabular method works, I'm going to use a, I should probably use some trig. Let me come up with a good problem. Okay. Cool. So the one we'll use, remembering our integral of u dv equals Sunshine minus Voodoo. That's great. Okay. So what we're going to use, how about, ooh, I wonder if I can, just a minute everybody. This Dennis kid has no chill. Try not to get involved. Alright, yeah, let's learn some calc. I'm down to learn some calc. Okay. So here will be our tabular Hold on, I'm gonna go back to this implicit differentiation deal. Way back when. Oh, did I goof? I apologize if I goofed. I'm not supposed to goof. Going back to here. Oh, this isn't even the implicit differentiation. What did I mess up? I don't think I, Stefan, could you clarify? What part exactly you're talking about? I'm not sure, maybe I'm goofing, maybe I'm no, negative 60y over dx. I plugged in for y. I see y. I'm plugging in y equals 1 here, here. Y is positive everywhere, so I'm a little confused. I apologize if this is throwing anybody off. I'm looking at the scoring guidelines for it, and I'm not sure. Okay. Yeah. Okay. We're good. Never mind. Sorry for the hiccup, everybody. Okay. So going to just to get back to the tabular method. All right, guys, calm down. We're just doing some calc. Everybody's brain's fried right now. Let's not worry about it too much. Okay. So, if my computer loads right now, because I can't see my stream right now. Come on. All right, so what we're going to integrate here okay. What we're going to integrate here is, let's do x squared sine x. All right, so what we see here is, again, we have x squared, which is something we can easily take the derivative of, and sine x, which is something we can easily integrate. But with a little bit of foresight, we can see what we're going to end up with is, at the end, the integral of probably negative cosine x times 2x, which is just going to give us another thing that we're going to need to integrate by parts. So to avoid that, typically you'll see that you're almost always going to see this with something x squared or x cubed or x to the fourth or whatever times either a trig function or some like e to the x function that no matter how many times you take its derivative, you're still going to have either a trig function or an e to the x in there. There's a shortcut for this called the tabular method, and I'll explain how that works. Basically what you're going to do is take the u that you have and the dv that you have right off the bat, the things that you identify. This u will be our x squared, and our dv will be sine x. And you're going to want to basically continuously, here, I'm going to use my pink again. This will be so here you're going to want to take the derivative of whatever's currently in this column moving all the way down. Here you're going to want to continuously integrate it. And that's going to be done until this column reaches 0. So to show you what that looks like for this function, x squared is going to go to 2x, which is going to go to 2, which is going to go to 0. Now over here, we're going to have sine x, which will go to negative cosine x, which will go to negative sine x, which will go to cosine x. Next, we're going to put signs in the middle here. We're going to start with negative. This is the part that's a little bit memorize-y. What you're going to do, hey.
This is going to happen one time.
What you're going to do, thank you.
One time.
What you're going to do is minus plus minus. And then if you're going further down, you would continue that pattern of minus plus minus plus. Finally, what you're going to do is look at these diagonals. And the sum of those things multiplied, this is sort of like a complicated way to word this, is going to be the solution. So what we're going to do, this first thing that we see is going to be x squared times negative 1 times negative cosine x. That will give you x squared cosine x. Next we'll have 2x times negative sine x. So we'll have minus, or 2x sine x, I misspoke, sorry. Finally, minus 2 cosine x plus c. And that will be your integral. Basically, you're taking the product of these diagonals and summing them all together. What I'm going to do real quick, wait, hold on. To answer someone's Reddit question, you're going to use the tabular method when, basically, if you start to use integration by parts and you see that the integral that it produces, the voodoo part of the sunshine minus voodoo, when you see that that's going to produce another integral that will require integration by parts, that's when you know you want to use tabular. To sort of identify it right off the bat, you'll see a common pattern with things that appear in the AP exam, and that's generally going to be something x to the something times something that when you take its derivative repeatedly, you get something that's never going to reduce to 0. Basically, one thing that's going to reduce to 0 and one thing that's not. So I'm going to do one more integration by parts with the tabular method to sort of cover exactly how that's going to work. Yeah, basically a polynomial with exponential or trig. Yeah, that's correct. Tabular only works if one of the terms is a polynomial, which means it will reduce to 0 when you take its derivative repeatedly. So I'm going to show one more time what this looks like. You can use tabular every time. It's kind of weird and you might get a little confused if there's only one row as to like what's going to be negative, what's going to be positive, or whatever. I'd say if you have an exponent that is 2 or greater, then knock yourself out. Go and use tabular. So what we're going to integrate now, I'm just going to do a long one just to show you exactly how this works. We're going to do let's do 5x to the fourth e to the okay. So this one's going to get messy, but we're going to take care of it. So basically, we see this 5x to the dx. This 5x to the fourth term, that's our polynomial. That's what's going to reduce as we make our way down the tabular column. Yes? So we'll put u here, dv here, 5x to the fourth, and again we're going to differentiate. Here we're going to integrate. So 5x to the fourth, oh, this is going to be crazy, 20. So that's what's going to go down there. And for dv, we're going to start with e to the 2x. That's going to go to 1/2 e to the 2x. Basically, we're just going to repeatedly integrate. 1/4 e to the 2x, 1/8, so on and so forth. And now we're going to fill in with that minus, plus, minus, plus, minus, plus garbage. So we're going to start with a minus in here, plus, minus, plus, minus. And then just to highlight the columns real quick, actually, I think a highlighter would be useful for this. So just to sort of show how that's going to work, we're going to go basically down these columns. This is integration by parts, so this is BC to all of you AB people that are out there somewhere frantically wondering what the hell is going on. I'm gonna Alright, so we're going to take these things and just here, one moment. Alright, I'm back. So, first of all, I need to fix something. Because I messed something up. I have to explain integration by parts. The the pattern of the plus minus that I gave everybody was incorrect. Cue like some disappointed noises. Excuse me. Okay, so this deal in the middle here with the minus plus minus. I'm sorry, I failed you. Cody High came back to haunt me. We're going to take these signs in the middle here, and we're just going to flip them. It starts with plus. Plus, minus, plus. Oh, my bad. I didn't have the mic near my face. It should be fixed now. So that's going to cause all of our signs out here to flip. Yeah. Okay. So yeah, it starts with plus. The first one that you're going to use is plus. I'm sorry that sorry for any confusion that I caused. I'm sure it caused a lot. I'm sorry. Yeah, it starts with plus. It goes plus, minus, plus. So, yeah. Sorry about the goof. Franz, everything I've done is like on the bar on the side, you'll see. Yes, Nitin, there will be a series problem done here later. I have one from a test a couple years ago that I will get to. I thought... No, you're gonna start with plus. Yeah. So going back to this last problem, that's gonna mean a little bit of a different situation for all of these. We're gonna change this to so what this is going to give us once we now that we've taken care of all of our signs, this is going to give us our final answer, which will be absolutely disgusting. I'm just going to write it down here. (60/8). What's second link over 2? 15/4. Uh, 120/16. These get harder. 15/2. Ethan, for separated differential equations, you can go to the link at the bottom of my screen, or to the Ethan. I did something just like that. Just go to the. I'm not done, Stefan. Don't worry. Don't freak out on me yet. I'm just making sure that I'm doing all this math right, because I'm doubting myself right now. 60/8 definitely goes to 15/2. I'm a dunce. I'm gonna chill with the C stuff, everybody. I'm gonna get there. Okay. Just making sure, just checking my math. Then we're gonna have. Oh, that's not bad. Okay. And our last term will be plus 120 over 32. But that's just going to be, that's the one that's 15 over 4. Plus C. I hope you're happy. Cool. There you go. Here's your disgusting integral. That is, I'm going to go ahead and call that, I'm going to call this guy probably right. Yo, what's up, Megan from Newspaper? Oh, dang. A lot of us are here from Reddit, Ethan. I posted this on my Snapchat story, so there are a couple kids from, or I didn't post it on my friend posted it on her Snapchat story, and so a couple kids are here from my school that are taking this test tomorrow. It's pretty cool. Have 80 people watching this. Alright, so, yeah, it's probably... Oh, Vera! I hope you didn't miss my straight line earlier. I shouted you out. Yeah. Alright, cool. I'm going to scan this integration by parts thing. Scan this integration by parts thing. Put it on the drive, and we will move on. I am from Florida. I won't mess up, Ethan. Punk. Okay. Ethan, it's going to be on what I just went over, the integration by parts. That will certainly be on Calc BC. It will not be on Calc AB. Most critical series tests, I would say the limit test and probably the ratio test. Limit and ratio will get you, like I've taken a couple mocks for this. I mean, I've taken this test already. I got a 5. But the most common things that I've seen across all the tests I've looked at, limit and ratio are going to get you, they'll get you a long way. I'm pretty sure everything will be doable with limit and ratio. Now, I don't want to don't come crying when for some reason you need to use a different test later, but that's just been my experience. Oh, shoot, I forgot to scan the other side of this. I goofed. Always goofing. Ethan, what I just did, that whole zigzaggy thing you saw, that was the tabular method for integration by parts. Lagrange will be on the test. Man, if I'm going to talk to stuff in the chat, I feel like I should probably just type it in the chat, because it takes so long to actually get to you guys. There's a freaking ridiculous 30-second or some shit latency between me doing something and it getting to you. Okay, so integration by parts is about to be up on the drive. What I will say is, if you know one thing for this test, That's going to be your most helpful tool. Yeah, so basically the logic behind this is if you get a 1 on Calc AB and a 1 on Calc BC, you've wasted 3 years of high school. That's the logic behind that equation. Okay, so now we're going to move into L'Hopital's and Riemann sums and junk now that we've done some Calc BC stuff. We will get to series. I know everybody's freaking out about series. Yes, we will get to series. We will get to series. Okay, so what am I going to do next? Okay, integration. We did integration by parts. Let me change the to do. It's like one big freak out, isn't it? Cool. So, also, many thanks. Someone just someone gave me Reddit Gold, and I don't know who you are because you left it anonymous. But whoever you are, thank you very much. It means a lot. I'm glad this is appreciated by everybody. Cool. So let's have a look at L'Hopital's rule. L'Hopital's rule is going to be super cut and dry. Okay. Nice and simple for all of you AB people out there. Basically, L'Hopital's rule. Yeah. SEMrush, I've added a link up at the top. If you're actually interested in doing that, that'd be cool. So, yeah, that's there. All right, so let's have a look at L'Hopital's rule real quick. I'm going to find a couple problems for it. See if I can. All right, so here's a couple practice problems. So L'Hopital's rule, basically the idea, the motivation for L'Hopital's rule is if okay, so this is basically the golden. This is the idea. This is what we're rolling with here. So if you have something like this, I'm just going to give a couple super simple ones. Basically, if you have like the limit, let's say as x approaches, I don't know, 0. This is a classic one of sine x over, let's just go x. When we plug in 0 into this, the first time we try, before we use L'Hopital's, we're going to have sine of 0, or 0, over 0. But that's no good. We can't have that. So we can basically rewrite this and say this is going to be equal. We can do the same thing. We're going to keep the same limit. That is, x is still going to go to 0. And we're going to take the derivative of the top and the derivative of the bottom. So this will become cosine x over x, or cosine x over 1, because we've taken the derivative of the top and the derivative of the bottom, a mouthful. And now when we plug in 0 for each of these, we'll get cosine of 0, which is 1, over 1, and this will be our answer instead of I can't speak right now. I'm sorry. It's teacher. Liam, if you want to learn what integration by parts is, you can go back in the video. I covered that. It looks like it starts at like just like go back in the video and you can find integration by parts. Also, if you go to that if you go to the link at the bottom of the screen, the jmag.me/calc review, that will bring you to the integration by parts page that I wrote. Yeah, so this is going to be very important question by Newmate City right now. You don't take the derivative of the whole thing. That's going to be I'm going to put that in big letters. That's getting some emphasis right now. Yeah, so you're going to take the derivative of the top and the derivative of the bottom separately. So yeah, thank you, Stefan. So let's look at something like, hold on, let me come up with something off screen real quick. Okay. Oh, I cheated. Womp womp. Or like you can see it. But whatever. Okay. So let's say we have this. The limit as x approaches 4 of these two polynomials. Now, if we just straight plug in 4 into these, let's just see what we get. We'd get 16 minus 4 minus 12 over 16 minus 8 minus 8, and oh shit, that's going to give us 0. Oh shoot, sorry, is going to give us 0 over 0. That's going to be, that's going to make us be like. So what we can do is take the derivative of the top and the derivative of the bottom separately. So we're not going to do the quotient rule where we do ho-de hi minus hi-de ho over ho-ho, that garbage. We're not going to do that. What we're going to do is this is going to go, we're strictly going to take the derivative of the top, which will become 2x minus 1, and the derivative of the bottom, which will be 2x minus 2. Yeah, I apologize, I got a potty mouth. Okay, so now what we can do, this is the new thing that we're going to be taking the limit of. So we'll have the limit as x approaches 4 of 2x minus 1 over 2x minus 2. That'll be equal to, which if I'm not mistaken is 7 over 6. Which is, yeah, cool. Alright, nice. Yeah, that's good. I'm gonna put that in a little pocket down here. Actually, you know what? Yeah, cool. We're good. I'm not gonna muddy this up anymore. Okay, so that's the idea for L'Hopital's rule. I'm going to keep that concise. Cool. I'll scan this and upload it ASAP, and we will move directly into Riemann sums, and then into U substitution, which is going to be good for everybody, because everybody needs a little U substitution in their life. Oh no! What do you hear, Ethan? There's a lot of stuff going on in my house, so it could be maybe a TV. Okay, so L'Hopital's is saving. Namisha, it has started. We've done a bunch of stuff already. If you want to go back through the video to review things that we've already gone over, you can look at all of the problems that we've done at that link at the bottom of the screen. And to whoever said that thing about L'Hopital, I bet you think you're real original and hilarious. Super proud of you, L'Hopital. Some garbage. Oh yeah, no problem, Namisha. I'm gonna be going hard for like the next 4 hours. Calcing it up. As long as people are here, we're doing it. Oh man, look at this. 120 people watching. This is sick. Alright, cool. Yeah, I'm famous! Woo! Alright, cool. So, let's do some more calc. Let's adjust this to-do list. Yo, if you guys, here, I'm gonna just do a shameless plug in this chat. I'm super into Reddit Karma. I mean, I'm not actually into Reddit Karma, I don't care. But if anybody wants to, alright. Okay, so let's have a look at Riemann sums. We're going to do Riemann sums not only with, wait, hold on, someone just sent me, I have to print out some of these messages that I'm getting on Reddit. This one I have to print out. And one moment, just getting everything ready. I'm going to be teaching calc all night, Namisha, it's happening. To the person that just sent was go. Okay, we're going to do properties of this series that this is taking a long time to load. To everybody that just sent me something on Reddit, I will go over those. Oh wait, shoot, did they ask for a particular? Okay, question 2. Okay, that was a solids of rotation problem. Okay, we will get there ASAP. Dang, I have received 2 cents on my PayPal. Someone has donated a cent 2 times. That's crazy. That's wild. Thank you so much. You guys are so generous. Alright, so we're going to, I'm printing this out. Alright, sick. So let's have a look at Riemann sums. I'm going to do a Riemann sum with both a chart and an actual function. So, alright. So, for a Riemann sum, there's going to be a couple different ways to... What the heck? What just printed? Hold on, my printer's being awfully silly right now. Okay, so this one I'm going to do. Alright, how many upvotes do we have right now? I'm gonna go venture a look. See how we're cooking. Damn, 35? Sweet. Alright, yeah, we're gonna do some more calc. Let's go. Let's do Riemann sums. Okay, so Riemann sums will generally be given in, there are like a couple different ways that you can get them. You can get left Riemann sum, right Riemann sum, midpoint Riemann sum, or trapezoidal Riemann sum. The way that I'm going to explain this right now, I'm going to go over a super basic conceptual explanation of Riemann sums, and then I'm going to show how to do a trapezoidal Riemann sum using a chart. So we're going to do, or we'll do both of them using a chart. So the basic idea behind a Riemann sum is if I have a curve, something like, actually, I'm going to scrap this piece of paper. We're going to do Riemann sum. I'm going to do my, oh, yo, what's up? It's my little advertisement paper. Okay. Yes, we're doing everything. We're doing left, right, midpoint, trapezoidal, the whole 9. We're doing them all. Okay. So, first we will start by explaining what a Riemann sum actually is. And for that, I'm going to see if I can okay, I can get most of the paper in the picture here. Cool. I did integration by parts Liam. If you go back in the video, you can check out my explanation on that. So, okay. So for Riemann sums, what I'm going to do here is explain the... Oh, that was the least straight line I've done all day. Sorry to disappoint you, Vera. Okay, so I'm going to draw a curve. That is a... That's a... No. I'm wasting paper. I can't use that curve. That curve was atrocious. Hopefully I can make my line straighter this time. Still bad. My apologies. Okay, whatever. So, the more important thing is that I explain them, right? That'd be cool. So, basically, that's like the same damn... Whatever. Okay, so, I'm going to start with... Just like for sort of like a visualization of what a left Riemann sum looks like, we're going to have basically rectangles whose height is determined by the left point of the rectangle. So something like this. The area of these three rectangles would constitute the integral with a left Riemann sum here. Next we have the... Darn, so many colors to choose from. I'm going to do the right Riemann sum, which is kind of almost self-explanatory based on what I just gave you, but I'll do it anyways. So it's going to be basically an integral with rectangles using a right midpoint. So basically the combined area of these rectangles here that I've just drawn. Next we have the midpoint. Actually, I'm going to do trapezoidal here, just because it'll... this curve's about to get nuts. Only a nerd would ever use that phrase. Okay, I'm going to say... Man, I'm going crazy right now. Okay, so trapezoidal is going to look something like this, where you've got the area of these trapezoids making up the Riemann sum. That's going to be trap. And finally, we'll have the midpoint, which I'll do in orange. Which will look something like this. So basically this visualization should sort of serve as a guide for how the, you can leave everything unsimplified to answer that question in there. So we're going to do the equations for it. next. So, I'm not going to go over like the straight equation. I'm just going to go over to like how to calculate them. So this is important. We're going to get to polar integration in a little bit. So, okay. So you'll see a question like this. We're going to use my handwriting is just like completely disappeared in writing that problem. So using 4 subintervals of equal area, use a midpoint Riemann sum to estimate the area under that curve on the interval 2 to 4. So what you'll see when you get this 4 subintervals of equal area, you know you're going from 2 to 4. Since we're using 4 subintervals of equal area, we can kind of like use this little drawing that we've made. These are going to be the bases of our rectangles. Whatever our curve is going to be up here somewhere. But these are going to be the rectangles. Now, whether or not these are left, right, or trapezoid, we can sort of like work that out later. But basically, we're going to be, since this is a midpoint Riemann sum, if our curve is like, say, up here, we're going to be using the midpoint to estimate its that rectangle's height. So what we're going to be using here, this will be 2.25. This will be 2.75. That'll be 3.25. That'll be 3.75, and that you can just kind of figure out with a little bit of intuition. I'm going to get to BC stuff. It kind of just looks like it's going to come later, based on that to-do list. I will get to serious things though, moving as fast as I can. So the to make this estimate, we see that the subintervals are going to be 1/2 in width. So our estimation is going to be 1/2. Basically, we see like the area of this rectangle, this length here is going to be f at 2.25. So whatever our curve is, our y value of our curve at this 2.25 point, that's going to be the height of our rectangle, and the width is going to be equal to the length of the subinterval. So essentially, you can find the width of subinterval is going to equal so that's going to be an important thing. Here we're going from 2 to 4 using 4 subintervals, so our width is going to be 1/2. So here you have that width. Times our midpoints. So f at 2.25 plus f at 2.75 plus f at 3.75. This just got really sloppy real quick. I'm sorry if I'm losing anybody. Looking at the chat, it just kind of looks like it's a bunch of people babbling garbage, but that's cool. So, basically, you're going to want to go... Wait, hold on. Someone's requesting access to the Google Drive. Can anybody not see the Google Drive? Is anybody not able to view that link at the bottom of my screen? Oh, he was trying to edit it. No, you scammer. So I don't want to go like, whatever, I'll just evaluate it. So we're going to have 2.25, 2.75, 3.25, and 3.75. Darn, I really wish I had a calculator. That'd be super neat. I don't know. Wait, hold on. One moment. Okay, sorry about the disappearance. Yeah, I'm just gonna Wolfram Alpha this. I apologize for the delay. I'm gonna integrate from 2 to 4. Interval size is 0.5. Okay. Yeah. We're just waiting. We're just waiting for the answer to come through. And if you go evaluate this yourself, something left as an exercise. The answer is going to be 58. Oh, wait. Oh, that's left endpoint. I'm garbage. Midpoint. If you did all this yourself, you should get something like 67.875. I kind of gave up on that. The one thing that I'll show you how to do is wait, hold on. Let me just scan these two things first. While I pull this up. Yo, hold up. Oh man. I bet this is somebody from the stream. Hello? Hello? Say what? I think I just picked up the phone of somebody in the stream that called me. I'm dumb. Alright, we're gonna... Oh, wait, hold on. I said getting ready for next topic, but we're actually gonna do one more quick thing since I have this test already up. Let's print out... Alright. Basically the last thing that I want to explain for Riemann sums, just like super quick, is if you have a table that looks something like this, basically if you've got like if you've got a chart something like this, and it says basically what you're going to want to do, the difference between this and the other ones is that the widths of the intervals are not going to be the same for all of the intervals, because we see the difference between 2 and 3 is different than 3 and 7 is different than 7 and 9, etc. So since we're using a right endpoint, we're going to be creating a rectangle with this pair of points, with this pair of points, with this pair of points, and with this pair of points. And for each one, we're going to use I keep losing my pink pen. We're going to be using this height to estimate the height of the rectangle. So to Okay, so to turn this into a right endpoint estimation, what we're going to do is say our first rectangle is going to have a subinterval width of 1 and a height of 3.3. That will be our first rectangle that we're using for the estimation. Next will be the next, here, let me illustrate this a little better. This will be 1, 4, 2, and 10. And we'll be using these numbers on the bottom as the heights of our rectangles. So 1 times 3.3 plus 4 times 9.7 plus 2 times 4.2 plus 10 times 11.6. And if somebody has a calculator, that would be super. Super. I sound like an idiot. Okay. Let's see if anybody can beat me to it. I'm getting 166.5. And for the, oh, did I goof? Did I actually goof? Mohan doesn't know how to use a calculator. Good job, Mohan. You're a freaking goofball. Okay. The last, very, very, very last thing that I want to touch on is if you forgot how to find the area of a trapezoid. If we're doing the same thing up here, but with trapezoidal. If you have something like this, you need to know this. If you have that's going to be the area of that rectangle. Unless I goofed, but I don't think I goofed. So to do the same thing again with these values that we have up here, can I make this go up any higher? I don't think so. Oh, but I can, no, I'm not going to do that. That just gets hard to see. That's fine. Then I'll have something like yeah, so that there, and this is where I challenge the, this is where I need confirmation again. The other one was some small potatoes. If you guys could verify my answer on this one too, that'd be super. Because I just do not. Alright, if anybody else did this, the one I'm getting is 121.8. Oh, sick! Me and Namisha got the same thing. Awesome. So we know we did something right. Alright, so that's the idea. I'm going to put all this Remon stuff up on the Google Drive, and we will move right into USub. Sick! People are talking about some ridiculous trap rule thing. I don't know if I said trap rule. Andrew, I'm the only one that can send links on here. If you put a bunch of spaces in the link, or replace all the periods with, like, I don't know, equal signs or something, and then other people can replace them if they want to, that works for getting them through. Andrew, I did. If you're talking about separable differential equations, I have already done those. I'm thinking I'm going to do a logistic one, just because I think I might do a logistic one before I move on to another thing. Possibly, possibly not. Yo, I'd like to shout out again whoever donated a single penny to that PayPal donation thing. You're the shit. Okay. So I actually hold on, I'm about to dip. Okay. Everybody here, I'm gonna take 5. Go get a drink, come back. I'll be here at 9:30 p.m. Oh shit, I messed up, Vera. My bad. Yes, I'm gonna get Lagrangian series stuff. That's like the next phase. I'm getting all the AB stuff out of the way. Nope. Bad, bad, bad. Bad, bad, bad. Man, my lines are just off today. I apologize, Vera. I apologize. Alright. Alright. EST. EST. I guess I'll clarify. I'm an East Coast kid. Alright, let's get it. I'm back. Here we go. Welcome back to some calculus. Welcome back to some calculus. We're gonna do some calculus, featuring probably the most straight line I've ever drawn. Look how straight that line is. Yo, if that's the straightest line you've ever seen, drop a like and a subscribe. Can we get this video to 500 likes? Do you think we can get 500 likes? No, I apologize. I wish I could. Maybe I should just stop the stream right now. Oh well. Okay. Let's do some USub. Let's learn about USub. Yeah, smash that like button. Okay. Joseph, chill. All right, here we go. Yeah, I'm an official professor. I've been professing my failure to be a good student for many years. Okay, but for real, let's do some USub. U substitution. Because apparently some people are like, "What the heck is USub?" We're just gonna do a quick USub. We're gonna do a couple quick USubs. Dennis, don't worry, I'm not forgetting it. You see the to-do list? If anybody is freaking out about the series question, have a look at the to-do list on the side that has not gone anywhere. It's gonna stay there, and we're gonna make our way down to that series problem. So don't you worry. Maybe we should just move the series problem up. We're not gonna do L'Hospital's rule. That's why it says done for rewind. All right, we're gonna do USub. So here, we find a solid USub problem. Okay, this is like the most basic thing of USub that there is. All right, so the idea behind U substitution is that you're going to find some term, some function within your integrand that has its own derivative also inside of the integrand. So if I have something like, let's say, basically, what a fool would do is FOIL all of this out, take this to the fourth power, bring it all the way out, and then just basically apply the power rule to each individual term that you would get out of that. That's not what we're going to do. What we're going to do is identify that this here, if we let this equal, like let's say everything that I have underlined, if I let that equal U, let me figure out for a minute what du would be. If I have U here, or I should say the derivative of U with respect to x, the derivative of U with respect to x would equal 3x squared plus 2x. So we notice something interesting. This term, this 3x squared plus 2x, exists right here in our function already. So I can change this. I'm going to move this around a little bit, and I'm going to say du. Actually, let me do this in blue. Du equals 3x squared plus 2x dx. And that is this thing that I'm underlining right now. I know this is easy stuff, but the reason I'm assuming that the people that are calling this easy stuff are people that are in Calc BC, and there are people here that are in Calc AB where U substitution is one of the things that they learn later in the year. So I'm going to be here all night. So if you guys, I'm assuming the people that are in Calc BC are mature enough to push their bedtime back a little bit for the sake of studying for a test. So I'll get to the series stuff. Don't you worry. We're going to get to polar areas not too far away. I'm probably going to move some of these things around. I'll move some of the Calc AB stuff, shuffle it in with the Calc BC stuff so that we can hit everything. But basically what we're going to do is change this into the integral of u to the fourth du. And this we know how to integrate using regular like power rule for integrals techniques. That's going to be 1/5 u to the fifth plus c. And so now all we need to do is take this u and plug it back in to this form. Was that kid that was like, man, this is too easy? Do you even know how to, like, did you math right? Some kid, whoever said this was like super goofy and like too easy, I think you got this wrong. I may be wrong. I may be goofy. But what we're going to end up with is 1/5 x cubed plus x squared and that will be our integrated. That's going to be our antiderivative, if you will. Man, Joseph DeLuna, you're a super goof. I would recommend going to Anti-Goof University and figuring out your life. Why is it to the fourth? It's to the fourth because I'm a silly person. That's gonna be to the fifth. Yeah, thank you for catching that. I was just testing you guys. Yeah, cool. So that's what's going on here. Cool. Yeah, no, I messed up. It should be to the fifth. I fixed it. Man, Joseph, go home. Okay, so U sub, I'm going to do one more U sub that's a little more complicated than this. I'm sorry, I feel like I'm getting a little too casual here. I'm going to try and bring it back for the people that are actually trying to study. Yeah, I always remember the plus C. So you'll also see, yeah, okay, this is good. So you'll see things sometimes, it won't always be as obvious as this. When you have things like polynomials, you can very easily identify what the antiderivative is, or you can very easily identify what the derivative is and what it is you need to change. But sometimes it won't pop out at you so easily, and I'll show you what that looks like. If you have something like, here again, we're going to identify a part of this integrand that has its derivative inside. Well, the first thing we're going to want to do is pull out all constants, and that will help the actual U substitution that we're going to do here pop out. So I'm going to rewrite this. I'm going to bring out this 2/3 to the front, and hopefully it will become a little bit easier to see what's going on. And if anybody hasn't seen it yet, I'm going to I'm going to rewrite this in one more way. I'm going to rewrite it as so what we see, what becomes evident here is this. If we let this ln x equal u, we know that 1 over x is equal to the derivative with respect to x of ln x. So this is derivative of u with respect to x. So just to sort of pull that out here, if I let u equal ln x, then the derivative of u with respect to x is 1 over x. So du will equal 1 over x dx. So now, if someone dies during the test, it doesn't do anything to you. It's no. Okay. So we're going to take this 1 over x dx and make that substitution up here. We're also going to change that ln x to a u. So what that will give us is, I'll keep this 2/3 out in front here, and we'll have sine of u du, and of course you know how to integrate that. That'll be negative 2/3 cosine u. And now all that's left to do is take that, take our u and plug it back in. Do not leave the u in the formula, or do not leave the u in your antiderivative. Yeah, you won't get credit for that if it's on a free response. So our final answer will be negative 2/3 cosine ln x plus c. All right, cool. So that's going to be, actually, I'm going to do one more super quick u sub where I explain how to do a u sub for a definite integral, and I'm going to make it a hard u sub for all you people that are complaining. Aura speed. Aura speed! Oh, it's aura speed! Aura speed, could you elaborate on what you mean by summation? Etienne Ichkakovich, Etienne Ichkakovich. Hoping I pronounced that right. I'm gonna do u substitution for a definite integral, and I'm going to explain exactly how the bounds need to change in that instance. Yeah, okay. One more u sub problem, and then we're going to move on. I'm probably going to pull the solids of rotation out to the front and explain shell method. Did someone mention that shell method was not on this test, and I'm not sure if that's true? Can anybody vouch for whether or not that's actually a thing? Okay. You cannot Yimong, you cannot use shells for what you can with disks. I'll explain that a little more in depth. Or actually, I'm not going to explain shells because we don't need. Okay. All right. Yeah. Thank you for the clarification, guys. Guys and gals. All right. So a quick u sub for a definite integral. Hold on, real quick. I'm gonna. Yo, you guys are upvoting my freaking... Okay, so u sub for a definite integral. Okay, yeah, trig sub. I will add trig sub to this list. Should I do just getting a quick testing the waters here? Should I do a trig sub for the next problem since I've just done u sub? Should I do trig sub? I know that is something that will be on Calc BC. Is that something that you guys are interested in seeing? I've gotten a couple requests for trig sub. Okay. All right, I'll do trig sub next. All right. I said I would do one more. All right, so this is the okay, I'll add trig sub. Okay, so I'm going to do this real quick. This is a definite thing with u sub, and this will be this is going to be a little bit different than the ones that we've done so far, because the ones that we've done up until now have been so everything's been exactly right there. This one we're going to have to modify a little bit, so I'll explain. This one we're going to integrate from 3 to 5, 4t over 2 minus 8t dt. Okay, so 8t squared. Yeah, this will be good. Okay, so hold on, I'm going to bring this in for anybody that can't see it. There's like a power surge going on with my laptop right now. I don't know if it seems like it's not able to handle my keyboard or mouse doing anything. Okay. Okay, as long as the camera stays in place. Okay, so what we're going to do here is, or again, what I like to do is pull out the constants right off the bat. So I'm going to take this 4. I'm actually going to, I'm going to take the 4 off the top and I'm going to factor a 2 off the bottom. So this will become Alright, so the way that we're going to approach Stefan, I'm going to do an optimization FRQ when I get to optimization in the to-do list. I'm on my way there. So what I'm going to do is let this bottom part here. Actually, this is kind of reminiscent of a trig sub problem, but we're going to do it with u sub. So this this bottom part here, we're going to let this equal, we're going to let this equal u. So doing the same thing we did before, we have u equals 1 minus 4 t squared. We'll do our du dt. That's going to be equal to negative 8t. So again, we're going to solve for du. Du is going to be equal to negative 8t dt. So now what we're going to do, we see that what we have in our integral is just that t dt part, right? Everything else is a constant. Or everything else down here is a constant. So what we're going to do is isolate that t dt in this equation. So we're just going to do one more step here and say our t dt is going to be equal to negative 1/8 du. And this is going to be the substitution that we make up in our original integral. So now we're going to have to remember that we're working with a definite integral. So because we're working with a definite integral, these bounds are not going to be the same when we convert to u. I'm going to show two different ways to approach solving this problem. I'm going to show once with modifying the bounds and once not, just so you have a, just so you understand. Okay, so this is, after making our substitution, we have 2. I'm going to leave the bounds alone for a second here and rewrite what I've got. T dt is going to be replaced with negative 1/8 du. So I'm actually going to rewrite this as 1 over u to represent the 1 over 1 minus 4t squared. And replace the t dt with that negative 1/8 du. I can bring that negative 1/8 out to the front. So now we have negative 1/4 integral of 1 over u du. So now, these original bounds that were on our u sub were in terms of t. So what we have to do, did I goof? I don't think I goofed. Did I goof? Someone's asking me about 1 over u. I should clarify a little bit more than I did. This here, what I'm going to circle right now, this is 1 over u. Just that denominator, and the invisible 1 that exists on the top of this fraction. That's the 1 over u. And I replaced the t dt with this negative 1/8 du. So I'm just separating it. Okay. So these bounds that were originally in terms of t, in this equation down here, or I should, in this equation right here, everything in terms of u, we're going to take, basically what we're going to do is we're going to take these bounds and plug them into this equation, this u equals 1 minus 4t squared. So when I take this 5, our bound in terms of u, which I'll just say u equals 1 minus 4 times 5 squared. That will be our upper bound. And so that's, what's that going to be? Am I being like completely? It's 1 minus 100. I can't do math. So that'll become negative 99. And our lower bound will be u equals 1 minus 4 times 3 squared, which 36, 1 minus 36, negative 35. So this will be negative 35. So now all we're left to do is evaluate this integral. And we don't have to do anything else. We don't have to convert our antiderivative back in terms of t like we did with the other ones. All we have to do is say negative 1/4 times ln u evaluated from negative 35, or I should say the absolute value of u from negative 35 to negative 99 is going to be our answer. So negative it's going to work out, to the people that were asking about negative 35 being bigger than negative 99, remember that this is going to be, we're going to take the absolute value, because that's the nature of the 1 over u. Okay, so I've spent too long on usub. I'm going to upload these to the Google Drive for my answer, or I'm going to upload these to Google Drive so I can move on to trig substitution. All these things that people are saying in the chat, I'm seeing a bunch of different ways to approach that are like perfectly valid, and that's cool. Yeah, I'm not going to go over derivatives today. My apologies. Okay, so the U sub stuff will be up momentarily. If anybody here doesn't know what that link at the bottom is, it's a link to a Google Drive that is everything that I'm writing on all these papers, I'm scanning and putting on the folder that's accessible from that link. So if you think something's kind of hard to see in the video, or you want to go over what I wrote in greater detail, you can do it there. And okay, U substitution should be up at that link now. Yeah, cool. All right, so wait, is trig sub? Trig sub, I'm almost certain is a thing on BC, so I'm going to go over it. I'm going to update the to-do list real quick. Trig sub is a thing on BC, so if you are... Okay, hold on. I'm going to move some things around right now, because there's the... Does anybody still need position and velocity? Do I need to go over that? Okay, I'm going to do logistic growth. I'm just going to replace position velocity with logistic growth. If anybody is not sure with that, put a bunch of capital letters in the live chat. Otherwise, it's just going to disappear. Yeah, yo, chill with the spam, please. Here, I'm going to do a, here's my 2-second explanation of position and velocity. Straight up 2 seconds. For anybody that needed position and velocity, here you go. Ready? There's your review on velocity. There you go. Okay, time to do trig sub. Okay, cool. So we have officially reviewed position and velocity. If anybody needed a more in-depth explanation, there's a guy named Sal Khan that can help you out with that. So I'm going to replace this with logistic growth. Cool. Okay, I'm going to just do a little bit of recon real quick and figure out if trig sub is on Calc BC. So I'm looking. Trig substitutions appear to be on Calc BC. Okay. From what I can tell, trig substitution is necessary for Calc BC. So I think, yeah, we're just going to do trig sub. Okay, I hope everybody's cool with that. Alright. we're just going to do trig sub. So trig substitution. Okay. So what we're going to do here, this is a BC topic, yes. I don't know if I should like write that on here, if that's important. But here's the, okay. So I'm just going to go over the basic logic of how trig sub works. So essentially, you're going to have, suppose you have an integral. Look, so I'm just going to be working through examples here because I have so many things that are still left to do. I know a lot of people are really bugging me to get to series. Yeah, here, yeah, that's what I'll do. I'm just going to label things in the to-do list A, B, and B, C, as someone in the chat's requesting right now. Okay. All right. So for trig sub, what you're going to have, I'm not going to skip to series. So for trig sub, what you're going to have is something like this. Let's say like okay, so this is what we got. For when you're doing trig sub and you see something that looks like this, something that looks like you're finding a side length with the Pythagorean theorem, you're going to want to take a look at what your numerator and denominator are. Generally, when you're working with trig sub, you're going to have a fraction that involves a square root, just for the sake of all the problems that you'll see in Calc BC that I've seen on all the practice exams. So what I want you to imagine doing is constructing a right triangle where you can sort of like, using this top term, come up with side lengths for this triangle. If I have that 36x squared minus 9, what that tells me is that I can make a triangle that looks like this, with some angle theta in here. If I were asked just to find what the length of this side is, I would do the square root of c squared, like if I called these a, b, and c, this would be the square root of c squared minus a squared, or 36x squared minus 9. It looks something like this. So, what that's going to help us do Okay, I'm back. Sorry for the disappearance there. So, essentially what you're going to want to do next is find a way to replace x using the triangle that you've constructed over here. You want to find some trig equation, some relationship with x that you can substitute into here. So the simplest one that we can get out of this is going to come from this 3 in this 6x. The first thing actually that I'm going to do is replace this. I'm going to pull that 1/2 out. So what we'll be left with is this. So we're going to look at our triangle here, and we're going to see what relationships we can find in x. So the first one that I see using cosine, if we take cosine theta, solving for x here, we can find that x is equal to 1/2 1 over cosine theta, or 1/2 secant theta. So now we have this relationship, this x equals 1/2 secant theta. So just using like regular Calc 1 differentiation, we can find dx So now we have this. What that's going to allow us to do, once we plug everything back in, is turn this into a much simpler equation that we know how to integrate. So plugging in this 1/2 secant theta into this equation for all x, we're going to come up with this. We're going to be replacing our right here. Hold on, just sit tight. So this numerator, this square root of 36x squared minus 9, when I plug that in, that's going to become 36 over 4 secant squared theta minus 9. Oh, sorry, it went off screen a little bit there. Man, I shout out Plugato. Super proud of Plugato for making it this far, for making it through the whole year. Really fantastic thing. So, okay. So what's going to happen up top here, this 36 over 4, that's going to go to a 9. And this will become, I'll deal with the denominator in a moment. That's going to become 9 secant squared theta minus 9, which should look familiar. This when I factor out this 9, which actually I'll just do in mind here, you should see something familiar. Secant squared theta minus 1, that's a relationship that's equal to tan squared theta. So this numerator becomes equal to 3 tan theta. Yeah, I just used whiteout tape, Matt G. Fight me. So basically replacing, I'm gonna replace this x on the bottom. I didn't replace it before. I don't know why. Secant theta. We're gonna replace our dx with this 1/2 tan theta secant theta that we found earlier. D theta. So we can see immediately these secant thetas will cancel out. This numerator up here, this 1/2, will become 3. Just to make it clear one more time, I'm going to take this relationship, this secant squared theta minus 1, and show you that's equal to tan squared. So with a little bit of simplification here, we can pull that 1/2 out, that 3 out, and we end up with 3/4. I feel like I messed something up somewhere with algebra. Where the 3 came from, after I found my x equals 1/2 secant theta over here using my triangle, when I substituted this 1/2 secant theta up into this equation, the 1/2 got squared, turning that into a 4, like 1/4 secant squared theta, which became 9 secant squared theta minus 9. I factor out the 9, and the 9 becomes a 3 after I pull it out of the equation. To who was it? Intense, that's like the same. Yeah. You're good. So that'll become 3/4 integral. That tan squared will just go down to a tan multiplied by that tan. Becomes tan squared theta d theta. So now this becomes something that we know how to integrate using just like typical Calc BC. So we can rewrite this as
Ah! Sorry, I don't know how that got changed into a 3 halves. And so now all that's left to do is take our original triangle that we drew and use the relationships on there to fill in our final integral. So tan theta, we can look at our triangle and see that that will be 3 over that disgusting thing. And then for the theta, you can just use something like, I don't know, you can take any trig function you want, any inverse trig function you want. I'll just use, since I've already been using tan, I'll just use tan inverse. Basically to represent that. And I'm going to check that with Wolfram. And hope I got it right. Okay, so I'm gonna slot this in. Does anybody want to do another trig sub, or is that it? I can do another one. If anybody wants like me to bang out another one where we do another, we approach it from a different angle, we can do that. Dang, I got another penny! I'm rich, yo. Thank you so much. I feel just so rich. Chill, Roshan. Roshan's so loud. I can't. The issue with series and all of the different rules that you have to do with series, I feel like I can't sit down and teach you every single rule that you need to know about series between now and the test. I can try. I'll do a couple free responses. Yeah, wow. It seems like a couple people want me to do series. All right, I'm gonna do. I think I might do a series problem. What do you guys think? Okay, so I think I have a genius idea for the next topic. I think I've come up with something truly revolutionary. So I think this is what we're gonna do. All right, here we go. So we're gonna do. Here's what we'll do next. All right, so this will be our next topic. Of course, I'm trolling. Where's my thing? Where's my card? Here we go. Okay. Sorry, the line. I'll bring back the line. There's a line. It's getting late for people on the East Coast. If there are people on the West Coast that are just tuning in, welcome. If you're on the West Coast, say I or something in the chat. I'm curious. Have they discovered this yet? The study session's not a troll, Manny. Let me just get my shit together. Thank you. Okay. I appreciate you, Ritvik. Okay. Here's what I'm gonna do. I found. All right. Dude, the count dipped to nothing. In like 2 seconds, it went from. Oh man. Wait, I dropped a pen. Hold on. Okay. Got it. All right, we back. Hopefully. All right. Oh, the count's climbing. It counts climbing. Okay. All right. So now, I don't know if you guys are. I don't know if you guys are into it, but I'm thinking I might do. Thinking I might do something with a series. solids of rotation problem, and then a related rates problem. I'm going to update my to-do list in that order, and that's going to be what happens. If you're not chill with that, find a different stream. Okay, now I have to remember what I said in the order I said it. That's what I'm going to do. Okay. I have calmed down, or I can't even speak. I have updated the to-do list. If anybody's not chill with it, you can go get your ass whooped by Kung Fu Kenny. Alright. Cynic Manic Panic, I imagine you can come back in about 20 minutes. 20 minutes would be cool, I imagine. I don't know. We'll see. Depends on how, much people complain. We'll see. Yeah, you guys beat me up. You should chill. Okay. Okay. Time. I gotta find a good problem from an old thing, and then we'll make it happen. Okay, I cannot for the life of me find an old problem that mentions an error bound. Can anybody find an FRQ that talks about error bound? Because it doesn't seem like you actually need to know. Okay, you know what? I'm going to do a problem. Do you guys want Maclaurin series? I'll do a Maclaurin series right now. 2008 second FRQ. Thank you to whoever said that. Wait, Form B? 2000. Okay, we're going to do series. It's going to be BC. I'm going to do this problem from the 2008 thing. Okay? Yes. Triggs, alright. We're going to do this 2008 problem 3 thing. Okay, I'm going to put this out and then we're going to do it. Finally. So, chill. Okay, I'm just going to... Actually, let's see if I can like superimpose it on the screen. Alright, here we go.